So we have discussed three methods for load flow, right? First one is the Gauss-Seidel method. The second one was the Newton-Raphson method. So this is abbreviated as NR. And finally the fast decoupled load flow. So this is abbreviated as FDLF. Okay. So now we will compare these three in terms of various parameters. The first one is the time required for each iteration. Okay, we are talking about not the number of iterations but the time required for one iteration. Okay, so the Gauss-Seidel method, it is going to take less time for each iteration, whereas Newton-Raphson is going to take more time for each iteration. The fast decoupled method, it is going to take the least time. Okay. Next, we need more number of iterations to converge. Okay, more number of iterations required to converge. Converge is nothing but to finally find the solution, right? And one more point here is the number of iterations required will increase as the number of buses increase. Okay, so number of iterations increase with increase in number of buses. In Newton-Raphson method, the number of iterations is less. Okay, and also it is not going to be much dependent on the number of buses. It is more or less going to be same. So that is why for huge power systems, Newton-Raphson is preferred. Okay, and fast decoupled load flow, it is going to take almost the same as the Newton-Raphson method. Okay. Next, accuracy. The Gauss-Seidel is the least accurate, while the Newton-Raphson is the most accurate. This is moderately accurate. So this here is the third point, right? Now the fourth point is, in the Gauss-Seidel method, the selection of slack bus plays a role in the convergence. Okay, slack bus selection affects convergence. Sometimes it may diverge if the slack bus is not chosen suitably. Okay, so here it is not going to make much difference in the Newton-Raphson method. Okay, slack bus selection doesn't affect much, and in fast decoupled flow it moderately affects convergence. Okay. Now the fifth point is, the programming logic is easy. We have to write a program for the computer to execute, right, for the system to execute. Now that programming logic, it is easier to write for the Gauss-Seidel method. Here in the Newton-Raphson method, it is going to be a little hard. Okay, so programming logic is hard. The fast decoupled method, also the programming logic is hard. Next, the last point is the memory. The Gauss-Seidel takes up the least memory, okay, storage in the system. Okay, whereas Newton-Raphson method, it is going to take up huge memory. Right, we have the Jacobian matrix, we are partially differentiating a lot of quantities with respect to a lot of other quantities, right? So it is all going to take up a huge amount of memory. Okay, What happens in fast decoupled? This is the major advantage of the fast decoupled when compared to the Newton-Raphson method. It is going to take much less memory compared to Newton-Raphson method. Why? Because two of the sub-Jacobian matrices we have equated to 0. Okay. So that is how the memory is going to be, memory that is required for fast decoupled flow is going to be less than the Newton-Raphson method. So these are the few differences between all these methods that we have discussed. Okay, so it is going to depend on the application. Whatever is required for that particular application, we are going to use that particular method.